We build our mental model of the universe around a comforting idea that the biggest things we know about are the limit of what is possible. The Sun is a massive ball of plasma, 333,000 times the weight of the Earth. Sagittarius, a star, the supermassive black hole at the center of our galaxy, holds 4 million suns in its grasp. These numbers are already beyond human comprehension. So we draw a line. We assume that somewhere there must be a ceiling, a natural limit to how massive, how dense, how old an object in the universe can be. But the universe does not agree with our ceilings. 10 billion light-years away, in a quiet corner of the sky most people have never heard of, sits an object that violates almost every assumption we make about how black holes grow. It is 66 billion times the mass of our Sun. Its event horizon is so large that it would swallow our entire solar system more than 30 times over. Its gravitational influence is so vast that the equations describing how it formed break down when we try to fit it into the timeline of a universe that is only 13.8 billion years old. It should not exist, not in its current form, not at the age we see it, not at the place in time it occupies. And yet, every night its light arrives on Earth. Ancient, distorted, impossible, a dim blue dot on a photographic plate carrying the signature of something that breaks our math. Tonight, we are going to the edge of what astrophysics can explain, a place where the universe stopped following the rules we wrote for it. This is the story of TON 618, the black hole that breaks the universe. Let's begin. In 1957, a team of astronomers at the Tonantzintla Observatory in Mexico were conducting a routine photographic survey of the northern sky. They were not looking for black holes. Black holes, as a concept, were still considered largely theoretical. The first observational evidence for their existence would not be published for another 7 years. The survey had a more modest goal. The team, led by the Mexican astronomer Guillermo Haro, was cataloging faint blue stars. These objects, distinguishable from ordinary stars by their unusual color signature, were of interest because they often indicated something physically unusual was happening. Hot young stars, dying white dwarfs, binary systems in their final stages. In the photographs taken over the course of the survey, thousands of these blue objects were logged, each one given a simple catalog number. One of them, in the constellation Canis Venatici, was entry number 618, TON 618. For nearly 2 decades, the object received no special attention. It was one faint point of light among thousands, sitting quietly in an archive. When astronomers looked at it, they saw what appeared to be a dim blue star, roughly magnitude 15.9, barely visible through a medium-sized telescope. Nothing about its appearance suggested it was anything other than ordinary. And then in 1970, radio astronomers revisited the archive. Radio telescopes had advanced significantly in the intervening years. A new generation of instruments was discovering a strange class of objects across the sky, objects that looked like stars in visible light, but shone with extraordinary power at radio wavelengths. They had been named quasars, quasi-stellar radio sources, and the scientific community was trying to understand what they actually were. When astronomers measured the spectrum of light coming from TON 618, the answer was immediate. The light was extraordinarily redshifted, not slightly redshifted, the way a nearby galaxy might be. Profoundly redshifted, stretched to a degree that could only mean one thing. The object was not a star. The object was not nearby. The light we were seeing had traveled an enormous cosmological distance to reach us. The calculations placed TON 618 at a redshift of 2.219. which translates to a light travel distance of roughly 10.4 billion light-years. To understand why that distance matters, you have to understand what a quasar actually is. When astronomers first discovered quasars in the 1960s, the data was almost impossible to reconcile. The objects looked like pinpoints of light, smaller than any star they could resolve, but they were producing more energy than entire galaxies. The physics didn't work. Nothing that small should be able to shine that brightly. The answer, when it finally emerged, rewrote our understanding of what galaxies are. A quasar is not a star. A quasar is the central region of a galaxy where a supermassive black hole is actively feeding. As gas, dust, and sometimes entire stars fall toward a black hole's event horizon, they form a rotating disk around it. This disk is called an accretion disk. Friction within the disk heats the infalling matter to extraordinary temperatures, hundreds of thousands of degrees, sometimes millions. Before that matter crosses the event horizon and disappears from the universe forever, it radiates. Across every wavelength we can detect: radio, infrared, visible, ultraviolet, X-ray, gamma ray, all at once. A feeding supermassive black hole can outshine every star in its host galaxy, combined by a factor of 1,000 or more. The galaxy itself becomes invisible next to the brightness of its own core, which is exactly why we can see them across the entire observable universe. We are not seeing the galaxy. We are seeing the last scream of matter before it disappears. TON 618 is one of the brightest quasars ever observed. Its intrinsic luminosity is roughly 140 trillion times the luminosity of our Sun. That number is not an exaggeration. It is not a metaphor. It is a calculation. If TON 618 were where Alpha Centauri is, just over 4 light-years away, its light alone would sterilize the Earth within minutes. Our atmosphere would boil away. Our oceans would evaporate. Every living cell on the planet would be destroyed by the radiation. But TON 618 is not 4 light-years away. TON 618 is 10 billion light-years away, far enough that its unimaginable brightness arrives at our telescopes as a faint blue dot, a pinprick of light screaming across the dark with the energy of an entire galaxy. For more than 2 decades after the distance was confirmed, TON 618 was known as an extremely bright quasar. But how massive the black hole at its center actually was remained an open question. The method for measuring the mass of a supermassive black hole was refined in the 1990s. It is called reverberation mapping, and the underlying idea is elegant. Very close to the accretion disk of an active black hole, there is a region filled with clouds of high-velocity gas. Astronomers call this the broadline region because the spectral lines of light coming from it are stretched or broadened by the Doppler effect. The clouds in this region are moving extremely fast, some toward us, some away. Their velocity is determined by the gravity of the black hole. The faster the gas moves, the more massive the black hole must be. By carefully measuring the width of the spectral lines and estimating the size of the broadline region, astronomers can calculate the mass of the central object. In 2004, a team led by the astronomer Roger Shields applied this technique to TON 618 using data from the Sloan Digital Sky Survey. The broad emission line of ionized hydrogen, known as H-beta, was unusually wide. The gas at the core of TON 618 was moving at roughly 7,000 kilometers per second. When they ran the calculation, the result was so extreme that Shields and his team published it with a clear note of caution. Further observations would be needed. The number had to be verified. Subsequent studies have confirmed it within reasonable error bars. The central black hole of TON 618 has a mass of approximately 66 billion solar masses. Let that number settle. Sagittarius, A star, the supermassive black hole at the center of our own galaxy, holds 4 million solar masses, already an incomprehensible weight. TON 618 is 16,000 times more massive than that. The black hole at the center of M87, the first black hole ever directly photographed in 2019 by the Event Horizon Telescope, holds 6.5 billion solar masses, one of the largest measured black holes in the nearby universe. TON 618 is 10 times more massive than M87. The category of black holes above 10 billion solar masses has its own name: ultra-massive black holes. These are the rarest monsters in the known universe. There are only a handful of confirmed examples. TON 618 sits near the absolute top of that category. To visualize what 66 billion solar masses actually means, consider the physical size. The event horizon, the boundary beyond which nothing can escape, is not a surface or a shell. It is a geometric limit where gravity becomes absolute. For a black hole, the radius of that boundary scales linearly with mass. For TON 618, the event horizon has a diameter of approximately 1,300 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun. The distance from the Sun to Pluto, the former 9th planet, is about 40 astronomical units. The distance from the Sun to the outer edge of the Kuiper belt is roughly 50. Our entire solar system, planets, asteroid belt, and Kuiper belt combined would fit inside the event horizon of TON 618 more than 30 times over. Light, moving at 300,000 kilometers per second, the absolute speed limit of the universe, would take about 15 days to cross the diameter of TON 618's event horizon. If you could somehow stand at the edge of that horizon and fire a photon directly across, it would take more than 2 weeks to reach the other side. There is no object in our cosmic neighborhood that comes close to this scale, and this is where TON 618 transforms from a fascinating object into a genuine physical problem. Because when we look at TON 618, we are not seeing it as it is now. We are seeing it as it was 10 billion years ago. Light travels fast, but it does not travel instantaneously. When we observe a star, a galaxy, or a quasar, we are always seeing the past. For nearby stars, the delay is years or decades. For nearby galaxies, the delay is millions of years. For TON 618, the delay is 10 billion years. The universe today is 13.8 billion years old. When the light from TON 618 first left its source, the universe was only about 3.8 billion years old, less than a third of its current age. And at that young age, TON 618 was already fully formed, already 66 billion solar masses, already producing the luminosity of 100 trillion suns, already an ultramassive black hole in the deepest sense. This is the problem. Our best theoretical models of how supermassive black holes grow are built around a concept called the Eddington limit. It was first derived by the British astrophysicist Arthur Eddington in 1926. The Eddington limit is a physical ceiling on how fast a black hole can consume matter. As material falls inward and heats up, it radiates enormous amounts of energy outward. That outgoing radiation creates pressure. If the radiation pressure exceeds the gravitational pull on incoming gas, the infalling material is pushed back. The black hole, in effect, chokes on its own light. The Eddington limit sets a maximum growth rate, expressed as the maximum mass a black hole can gain per year. If you run the math on how long it would take for a normal black hole, starting from a stellar mass seed of about 10 solar masses, to grow into a 66 billion solar mass monster while feeding continuously at the Eddington limit, you get a number. That number is longer than the age of the universe at the moment we observe TON 618. The equations, applied strictly, say that TON 618 should not have had enough time to reach its observed mass. At 3.8 billion years after the Big Bang, it simply shouldn't exist yet. And yet, it does. This contradiction has driven one of the most active areas of modern astrophysics for the last 2 decades. If the standard model of black hole growth cannot produce TON 618 in time, then something in the standard model must be wrong, incomplete, or missing. Several hypotheses have been proposed. The first is known as direct collapse. In the extremely early universe, conditions were very different from today. Vast clouds of pristine hydrogen and helium gas were scattered throughout the cosmos. Some of these clouds, under the right conditions, may have collapsed directly into enormous black holes, skipping the stellar phase entirely. Instead of a 10 solar mass seed, the universe may have produced seeds with masses of tens or even hundreds of thousands of solar masses. A head start of that magnitude would make it possible for TON 618 to reach its observed size within the available time frame, but direct collapse requires extraordinarily specific conditions. The gas must be almost completely free of the heavier elements produced by earlier stars. It must cool in a very particular way. It must avoid fragmenting into smaller stellar seeds. Whether the early universe actually produced such objects in significant numbers is still being investigated. Several candidate objects have been reported by the James Webb Space Telescope since 2022. The evidence is growing, but not yet conclusive. A second hypothesis is called super-Eddington accretion. The Eddington limit assumes a specific idealized geometry for the way matter falls onto a black hole. If the geometry is different, if the accretion disk is thicker, or if there are channels through which radiation can escape more easily, then the actual growth rate could temporarily exceed the classical limit. Some models suggest that early black holes, embedded in extremely dense gas environments, could have grown at 2, 3, or even 10 times the Eddington rate for extended periods. A third hypothesis involves mergers. The early universe was a chaotic place. Galaxies collided frequently. When two galaxies with central black holes merge, their black holes eventually sink to the center of the combined system and merge as well. Over billions of years, repeated mergers could produce increasingly massive central objects, faster than any single black hole could grow through accretion alone. All three mechanisms may have contributed. TON 618 may be the end product of an extreme combination of all of them. A direct collapse seed fed in super-Eddington bursts, supplemented by a long history of mergers. Or the answer may be something we have not yet considered. What is certain is that the existence of TON 618, along with a growing number of other high redshift, ultramassive black holes discovered since 2020, is telling us that our models are incomplete. The early universe was capable of producing monsters on a timeline our equations say should not have been possible. There is another layer to this that is worth pausing on. The TON 618 we study is not the TON 618 that exists now. The light we are analyzing left its source 10 billion years ago. By the time it reached Earth, the universe had expanded dramatically. Our solar system had not yet formed. The Earth did not exist. The atoms that make up your body were scattered across cosmic distances, part of earlier stars that had not yet finished dying. That light traveled for 10 billion years. Through the expanding fabric of space, its wavelength stretched by the expansion itself, through gravitational fields of galaxies long dead, through cosmic voids where nothing exists but hydrogen and faint cosmic microwave radiation. And then it reached us. So what we call TON 618 is, in a real sense, a fossil, a light fossil. The object itself, if it still exists, has changed. 10 billion years is long enough for any galaxy to transform completely. Its host galaxy may have merged with others. The supply of gas feeding the central black hole may have exhausted itself long ago. The quasar may have gone dark, starved of fuel, sitting quietly at the center of a much larger, quieter structure. Or TON 618 may have continued to grow, absorbed other black holes through galactic mergers, accumulated more mass through long feeding cycles. It may be significantly larger today than what we observe, or it may no longer exist at all in any form recognizable to us, having been part of some cosmic process we do not yet understand. We cannot know. Not for 10 billion years. The light leaving TON 618 tonight in the year 2026 will not reach any observer capable of seeing it for another 10 billion years. By that time, the universe will be almost twice its current age. The sun will have long since expanded into a red giant and collapsed into a white dwarf. The Earth will likely have been destroyed. The Milky Way will have collided with Andromeda and merged into a single, much larger elliptical galaxy. Whatever descendants of humanity exist, if any, will be unrecognizable, and only then will the light leaving TON 618 today finally arrive somewhere. We are not looking at an object. We are looking at an archaeological artifact, a photograph of the universe taken 10 billion years ago, still in transit across the cosmos. The distance between TON 618 and Earth is not just a distance in space, it is a distance in time. And time, unlike space, cannot be traversed. Even if humanity built a ship capable of reaching 99.99% of the speed of light, even if we launched it at TON 618's coordinates today, the journey would take longer than the current age of the universe. By the time any probe arrived, the object we were chasing would no longer be what we photographed. Some objects in the universe are beyond more than just our reach. They are beyond our relationship with them. We can measure TON 618. We can calculate its mass, its brightness, its composition. We can debate how it formed and whether our models are broken or just incomplete. But we cannot visit it. We cannot observe it in its current state. We cannot know whether it still shines or has gone silent or has become something else entirely. All we have is the signal that reached us. A dim blue dot in the constellation Canes Venatici, catalogued in 1957 as a faint star, revealed in 1970 as a quasar, measured in 2004 as the most massive black hole ever confidently weighed. 66 billion solar masses, 1,300 astronomical units across, producing the luminosity of 140 trillion suns, formed faster than our equations say it should have, observed across a gulf of time that cannot be crossed. A monster we know exists because its light reached us, and a monster we will never reach in return. Somewhere in the direction of Canes Venatici, north of the handle of the Big Dipper, there is a point of light. You cannot see it with your eyes. You would need a serious telescope and a long exposure just to register its presence. But it is there, and it has been there for at least 10 billion years. Not the largest structure in the universe, not the farthest object we have observed, not the brightest, but the most massive single object we can confidently weigh, an ultra-massive black hole at the edge of what physics allows, a ghost of the early cosmos, still shining, TON 618, the black hole that formed too fast, the black hole that weighs more than any equation allows, the black hole that breaks the universe.